In today's video, we are going to be taking a deeper dive into double integrals. This time though, we're going to look at general regions. So our region R is going to be some general region. It's not going to be a rectangle like it was before. So our objective is we're still finding volume using iterated integrals in rectangular coordinates. By rectangular coordinates, we mean our normal coordinate system XYZ. So we're going to look at some other coordinate systems later, but this video will have X and Y. So looking at our figures, before is what we did in the first video. So we had some function of two variables, and we had some region R on the XY plane, and that region R was a rectangle. And we mapped that region up, and we found the volume underneath our function. So what we're going to be doing today is that region R, in this case it's called D, is no longer going to be a rectangle. It's just going to be some general shape that, again, we map up, still looking at volume. And so these are a little bit trickier to set up and a little bit trickier to evaluate. So let's take a look at what that D could look like. There are two types of regions that D could be. We call them type 1 regions and type 2 regions. Before I go more into these regions, I'm going to let you know that this terminology is not helpful for me particularly. For me, this just confuses me. So I'm going to go through these two regions, but then practically when we get to our first example, I'm going to explain how I approach these and my understanding. So we are looking at double integral over the region. It actually should be D, not R, of f of xy dA. So the big question here is figuring out our limits of integration. So I'm going to integrate f of xy. Am I integrating with respect to y or x first? Well, we notice in this type 1 region, we have y in terms of x and y in terms of x. So we're going to integrate with respect to y first, then x. My lower bound for y would be g1 of x. My upper bound is g2 of x. And then my limits for x are a to b. In a type 2 region, so we have our double integral of f of xy. In this case, we see we have x in terms of y, x in terms of y. So we're going to integrate with respect to x first, from h1 of y to h2 of y, and then y, which goes from c to d. So you can see this is very different than what we did before when our region R was a rectangle, because our limits of integration were not functions, they were just numbers. It was a to b and c to d. But here, we're going to have functions. So if you're confused at this point, that's okay. Like I said, this vocabulary is not helpful for me. I think it'll be more helpful once we jump into our first example. So let's give it a shot. Example 1, evaluate this double integral where D is the region bounded by y equals 2x squared and y equals 1 plus x squared. So the first key here is we have to see what our region actually looks like. So we're going to have to start by graphing this. And if I were you, I would try to be very accurate as to what this region is that we're looking at. So if I start with y equals 2x squared, I'm going to go through 0, 0, and I'm going to go through 1, 2, and negative 1, 2. That's going to give me this blue parabola right here. So that is our y equals 2x squared. Then in green, I'm going to graph the second one, y equals 1 plus x squared. So we have y equals 1 plus x squared. Okay, so then we see that our region is this part right here. Okay, so in this case, we have a function y equals and we have another function y equals. So that might lead us to believe that we are integrating with respect to y first. And that would be true. Now, it's not always going to be that easy. So what I do is I like to look at my region. And I consider integrating vertically and integrating horizontally. So if we integrate with respect to y, if we go vertically, we notice the top part is always the green function, the bottom part is always the blue function, no matter where we go in our region. We're always going from green to blue, green to blue, green to blue. On the other hand, if we wanted to go horizontally, we would notice our left and right limits change. So I'm going from blue to blue, blue to blue, and all of a sudden I go from blue to green, or green to blue. Because my left and right bounds are changing, I would need to set up different integrals. In this case, though, if I go vertically, my lower bound and upper bound always stay the same, hence why we would integrate with respect to y first, the change in the vertical direction. So the lower bound is going to be our blue function, our 2x squared. Our upper bound for y is going to be the upper function, the 1 plus x squared. And then for x, we go to the leftmost point for x, the rightmost point, which is -1 to 1. So we're going to do some other examples where we're going to practice more of setting these integrals up, but that is the first step. Well, I guess really the second step. First step was drawing the picture. Second step was actually setting it up. So now what we're going to do is we're going to integrate like we did before, starting with the inner portion. So that -1 to 1 stays. If x is just a constant, because we're integrating with respect to y, we're going to get xy, add y squared. We're evaluating from y equals 2x squared to y equals 1 plus x squared, and then we have our dx. So continuing, this gives us -1 to 1 of x, add 1 plus x squared, add 1 plus x squared, quantity squared, subtract x times 2x squared, add 2x squared, quantity squared, all of that dx. And there's a lot of simplification. I've done the simplification for you. If you trust me, you get -3x to the 4th, subtract x cubed, add 2x squared, add x, add 1, dx. And now we're just back to integrating like normal, one integral, so we get -3/5 x to the 5th, subtract 1/4 x to the 4th, add 2/3 x to the 3rd, add 1/2 x squared, add x from -1 to 1. And that ends up getting us 32/15. And if you were asked what that meant, this would be the volume underneath this surface. So if z or f was x plus 2y, so this is the volume underneath this surface and above this region. Okay, so let's do another example. Here's this next one. We are going to set it up only, we're not going to evaluate. So evaluate double integral over the region R, where the region R is bounded by those 3 lines. Now, not a big deal if we use R or D, it doesn't really matter. So this case it used R before it used D. So don't get tripped up on that. Let's start by drawing our region R. So we have y equals 3. And then we have -x plus 1. This is not a super accurate picture, so please forgive my poor drawing skills. And then we have x plus 1, so similar idea. And there's our region. So we're going to have our double integral of xy, and we have to figure out, are we going to integrate with respect to x or y first? If we integrate with respect to y, so that means we would be going vertically. On the left side, we have a lower bound and an upper bound, and those stay consistent until we pass x equals 0. And then the lower bound changes. So on the left side, our lower bound is y equals x plus 1, but on the right side, it would be -x plus 1. ooh, sorry, that's backwards. This is negative x plus 1, this is positive. So that lower bound is changing, which what that tells us is when we get to this point, we would need to split our region up. And so we would actually need 2 double integrals. Now, that's not ideal. If we have to do that, we have to, but let's try to do the x direction instead. So if we try to do the x direction, we go left to right. We notice we are always going from y equals negative x plus 1 to y equals x plus 1. What that means is we're going to integrate with respect to x first, then y. If we integrate with respect to x first, that means we need x equals. So we need to solve both of these lines in terms of x. So this one will be x equals 1 subtract y. This one will be x equals y minus 1. Okay, so on the left, from this line right here, is 1 minus y to y minus 1. And then, in terms of y is going from here, which is 1 to up here, so from 1 to 3. And then you would solve from there. We're going to do more solving examples, so don't get too upset that we're not going to solve this one. Okay, let's do another one. So it's this one right here. Find the volume of the solid that lies under z equals xy and above d, where d is the region bounded by those two equations. So let's start by drawing our region D. So we have a line, and then this is going to be a parabola opening sideways. So we're going to start here, go here. So this is our line, y equals x subtract 1. And then we have that parabola. So that parabola is opening sideways, and it has moved 3 points to the left. So the point negative 3, 0 is on the parabola. If we substitute in a 0 for 6, we get y squared is equal to root 6. So somewhere between 2 and 3, same thing in the negative direction. So this is a rough sketch of our parabola. So our region is this one right here. So what I want you to do at this point is I want you to pause the video and try to set this one up. The biggest deal to me right now is, can you figure out, are we integrating with respect to x or y first? And then, can you take a guess at the limits of integration? So when you're ready, come on back and we'll set this one up together. Okay, so let's take a look at this one. If we integrate with respect to y first, we notice the top stays the same, the bottom changes. If we go left to right instead, left stays the same, so does the right. That suggests that we want to integrate with respect to x first. So we have the double integral of x, y, x first, then y. Okay, so on the right, our bound is that line, y equals x minus 1. So in terms of x, x will be y plus 1, so that'll be our upper limit. And then the left side for x is this parabola, which again we need in terms of x. So if we solve for x, we get 1/2 y squared subtract 3. So that'll be our lower limit. So then for y, the lowest y is this point right here. The highest one is that point right there. So maybe you drew a better picture than I did and you can clearly see what those points are. Maybe you have to solve for them. In my case, it looks like this one is 1, negative 2. The other one I can't tell, so I'm going to have to solve for it. So if I set my two x functions equal, I'm going to get y plus 1 is equal to 1/2 y squared subtract 3. Multiply everything by 2, I get 2y, add 2 is equal to y squared subtract 6. So hopefully this is going to work out for me, and I'm going to end up factoring, which would give me y subtract 4, y add 2. So my y is -2 and 4. So that -2 checks out. So this upper limit is y equals 4. And if you drew a better graph than I did, that upper point would have been 5, 4. Okay, and so here is where we are going to practice evaluating again, because this one is a little bit of a nasty one to evaluate. So let's start by integrating with respect to x. When we do, we get 1/2 x squared y from x equals 1/2 y squared minus 3 to x equals y plus 1. Now what I'm going to do is immediately, I don't want to deal with that 1/2, so I'm going to pull it out. So I get y add 1 quantity squared times y, subtract 1/2 y squared subtract 3 squared times y. So then I have y squared add 2y add 1 times y, subtracting 1/4 y to the 4th, subtract 3 y squared add 9 times y. Like I said, this one's pretty nasty. So y cubed add 2y squared add y, subtract 1/4 y to the 4th, y to the 5th, add 3y to the 3rd, subtract 9y dy. Okay, this is looking a little better. Combining like terms, I get -1/4 y to the 5th, add 4y to the 3rd, add 2y squared, subtract 8y dy. Okay, and we're almost there. Now when we integrate, we get 1/2 -1 over 24 y to the 6th, add y to the 4th, add 2/3 y to the 3rd, subtract 4y squared, being evaluated from -2 to 4. And if you got this far, I'm just going to tell you that our answer ends up being 36. As you can see, that was a lot of work, and so it's very easy to make a mistake. Obviously, if you have the problem set up wrong, though, you're never going to get the right answer. So it's incredibly important that the problem is set up correctly, and then that we are careful in our steps. So hopefully that one went well for you. Let's do a little more practice on the next page. So another thing that you have to be able to do is evaluate an integral by reversing the order of integration. So we see from this example, we are integrating with respect to y first and then x. Now the problem we see here is we cannot integrate sine of y squared. We can't integrate sine of y squared. So since we can't do that, what do? Well, in this case, we're going to try to reverse the order of integration. So we're going to try instead to figure out what are the limits so that we integrate sine of y squared with respect to x first and then y. Now, it's not just a matter of taking these and swapping them. That's not going to work. So instead what we have to do is we're going to draw our region. So these limits, remember, are y. So off to the side, what you have to be able to do when you're reversing the order of operation is the big one is you got to be able to draw the region. And then you can look at reversing the order. Okay, so we have y equals x. So that was not great. That's about here. And we're going from there to y equals 1. And then we also know that we're going from x equals 0 to x equals 1. So x equals 0 is here. X equals 1 would be this point. 1, 1. So this is the region that we're looking at. Okay, so if we want to integrate with respect to x first, that means we're going left to right. So we go from x equals 0 to our line, x equals y. And then for our y limits, at this point right here, y is 0, and then we go to y is 1. Okay, so we reversed our order of integration. Let's see if that helps us at all. So if we integrate sine of y squared with respect to x, so sine of y squared then is just a constant. So we're going to end up with x times sine of y squared from x equals 0 to x equals y dy. So then if we evaluate, we get y sine of y squared, subtract 0. So of course that's just y sine of y squared. And now we can integrate sine of y squared because we have that y out in front. So that ended up really nice for us. So we get negative 1/2 cosine of y squared from 0 to 1, which gives us negative 1/2 cosine of 1, subtract negative 1/2 cosine of 0, which is just negative 1/2 cosine of 1, add 1/2. Okay, so you might be asking yourself, when do I need to switch the order of integration? This is not a guess and check kind of thing. I will tell you, reverse the order of integration. So you will explicitly be asked to reverse that order. So we have one last thing to talk about, and that is area. So we can actually use a double integral to calculate area. So let's take a look at this figure that we have. We have this figure here where the plane is z equals 1, and we have some region D, and we're looking for the volume underneath that plane z equals 1 and above our region D. So then if we are looking for volume, in this case, it's going to be the area of that region D times the height of our figure, which is 1. So in this case, we get our volume is equal to the area of D. Okay, so what we've done before is volume was the double integral over the region D of f of xy dA. We want that to be equal to the area of D from above. Well, our function f of xy is just this plane z equals 1. So what that tells us is one way to calculate the area of a region is the double integral of 1 dA. So before, you had calculated area using a single integral. That's what you did in Calc 1 and 2. And now we can use a double integral instead to find an area of the same region. So let's take a look at this example. Use a double integral to find the area of the region enclosed between y equals x cubed and y equals 2x in the first quadrant. So start it like we do every problem, and that's by drawing a figure. So here is our y equals 2x, and then our y equals x cubed. So we're looking for the area of this region here. Now, please remember, this is not a very accurate picture. So it looks like both of these functions intersect at the point 1, 2, which is not the case, right? Y equals x cubed doesn't go through the point 1, 2. So just let's use a little bit of sense there. So if we want to find the area of this region in black, it's going to be the double integral of 1 dA. So we need to figure out, are we integrating with respect to x or y first? In this case, it doesn't matter. If we go vertically, our top bound and bottom bound stay the same. If we go horizontally, the left bound and right bound stay the same. I would suggest in this case we integrate with respect to y first and then x, because we have y equals and y equals. So the bottom bound is that cubic of x cubed. The upper bound is the y equals 2x. And x is going to go from 0 to whatever that point is. And we're actually going to have to find what that point is, since I didn't draw a very good picture. So we have x cubed is equal to 2x. So we're going to do a little factoring. So we get x equals 0 and plus or minus root 2. So hopefully you can tell based on the figure that that looks like a positive root 2. So then if we were to evaluate that integral, I'm not going to, we would end up getting the area of the region D. Okay, so that is the end of the required portion of the video. I have one last optional example for us to do if you want to do it. It has to do with reversing the order of integration. If you think you're good with that and you don't need any more practice, then you are free to go. If you want to look at one more example together, please look at the example on the next page. Okay, so again, evaluate by reversing the order of integration. And we can see we can't integrate e to the x squared. So we're going to have to start by drawing our picture. So this is our bounds for x. So we get x is equal to y over 2, or y equals 2x. And we are going to x equals 1. So I'm going to start by drawing those. So x equals 1 is here. And y equals 2x would give us this line. And then we are integrating from y equals 0 to y equals 2, which confirms we are looking at this region here. Okay, so we're now going to integrate e to the x squared with respect to y first and then x. If we go with respect to y first, we're going to be integrating vertically. So our lower bound is going to be y equals 0. And this upper bound is the line that x equals y over 2, or our y equals 2x. So we're going to go to y equals 2x. And x then goes from 0 to 1. So now if we want to go through the integrating part, we're going to integrate with respect to y first. Remember that e to the x squared then is just a constant. So we get y multiplied by e to the x squared from y equals 0 to y equals 2x. So that would give us then 2x e to the x squared, subtract 0. And this now significantly easier to integrate because we have that 2x. So this then becomes e to the x squared from 0 to 1. So our answer then is e to the first subtract 1. I don't know why I wrote it like that. So there is our answer. And if I asked you what it represented just for fun, this is the volume underneath this function e to the x squared and above this region D or this region R. So hopefully that was helpful. Moving forward, we're going to be looking at double integrals some more. This time though in a different coordinate system, not in rectangular coordinates. So I look forward to seeing you next time.